Hi everyone, welcome to Modern Optimization Methods. In this part, we will introduce the third part of Chapter 4, the Trust Region Methods. We will discuss how we solve the subproblem. We will mainly discuss the cozy point methods as well as the dogleg method. Now, recall that we try to find the approximate solution for the trust region methods. So the subproblem is like this. We try to minimize a quadratic function subject to a trust region radius. Then there are three ways to do the approximation solution. One is the cozy point, the second one is the dogleg method, and the third one is the two-dimensional subspace minimization method. Let's discuss with the first method, the cozy point. Now, the idea of cozy point is like this. So we try to use the steepest descent direction and then try to find out the solution in terms of if I walk along the steepest descent solution, then what kind of solution we can get. So the resulting point is called the cozy point. Now, the way we generate the cozy point is like this. Firstly, we first find out the model function with linear term and subject to the trust region radius. In other words, in the first step, we solve a linear model function optimization problem. Of course, we can find later that the direction is the same as the steepest descent direction. After we get the direction pks in the first step, then we assume that the scalar tau multiplied by pks is the solution of the quadratic function. Then we try to find out the optimal tau k, which is kind of step length. In other words, in the second step for cozy point, we actually minimize the quadratic model function by substituting the pk by tau pks. Okay? So it's actually a function only in one variable, tau. Finally, the cozy point is set as the tau k multiplied by the direction psk. Now, let's see how we can derive the cozy direction. For the first step, we can easily find that the cozy point is a way of steepest descent direction with a special step length. After that, let's put it into the model function and we do the simple calculation to find out that the model function related to tau is a quadratic function. So for this quadratic function, if we try to find the minimization, recall that we also got a constraint, which is tau smaller than 1, greater than 0. In this sense, we try to find the minimization. So the way we do is that we first discuss the coefficient of the quadratic term. Okay, so if the coefficient is negative, so together with the linear term, we can see that actually the model function in this case takes the following shape. So it is a quadratic function and also it is a concave function like this. All right? So recall that we are looking for the minimization problem within the interval 0 and 1. So in this case, tau equals 1 will be the minimizer. All right? So this corresponds to case 1. And if for the case 2, the coefficient is greater than 0, then the curve will be like this. We got a quadratic function with the shape like this. So in this case, if we try to find the local minimizer, then we only need to take the minimization of the minimizer as well as 1, okay? So whichever we reaches first, then it will be the minimizer of the quadratic function. So this gives the two-case solution. And finally, we summarize the result in this page. So this is the formula for Kersey point. In other words, Kersey point is actually have explicit form. Now we illustrate Kersey point by a figure. Now in this figure, we are standing at the current iteration xk, and the contours of model function is the ellipsoid here. So the Kersey point actually takes the steepest descent direction, and however, we restricted it to the step length here, all right? Because we are looking for the minimization along this direction. So the smallest function value we can get along this direction is here. So this gives us the Kersey point. Now, let's take a look at some remarks about Kersey point. So the advantage of Kersey point is that it has explicit form calculation, and it is crucial in deciding whether an approximate solution will provide good reduction or not, and whether we can get global convergence or not. So Kersey point is kind of bridge to set up the trust region method with the convergence result. We will see this later in the convergence part. And however, we may think about this issue that is there any way to improve the Kersey point? Because in Kersey point, we only make use of the gradient information, okay? So this may slow down the process. So is there any way to improve the Kersey point? So there are actually two ways to improve. The first one is the dogleg method. The second one is the two-dimensional subspace minimization method. In this part, we first take a look at the dogleg method. Now, the idea for dogleg method is as follows. So we first take a look at the subproblem, which is minimizing a quadratic function subject to some trust region subject. And we assume that for this subproblem, we take delta as the changing variable, and we denote the optimal solution of the subproblem as P star delta, okay? So as the delta changes, of course, the optimal solution will changes as well. So it's P star is a function of the trust region radius. From this sense, and we can see that if the matrix P is positive definite, then the direction PB, defined as the Newton's direction, okay? It is the minimizer of the unconstrained problem. Okay, so if we forget about the trust region restrictions, then we solve the model functions directly, then it will give us the result as PB is the Newton's direction, okay? So keep in mind the PB here, okay? So PB actually means the full Newton's step. Now, let's take a further look at different cases of delta, okay? So if this delta is greater than the length of PB, so in other words, Newton's direction is achieved within the trust region. So from this case, it actually means that the trust region problem reduces to an unconstrained problem, because we do not have to worry about the trust region radius, okay? Newton's direction is achieved within this trust region radius, all right? So in this case, P star delta will be the trust region step. However, if we change this delta to be very small, then sometimes we can make this PB outside of this trust region, okay? So in this case, this trust region constraints does take effect. It actually ensures that the quadratic term in the model function have little effect on the solution of P star. Why? Because the trust region radius is small compared to the model function, okay? Or in other words, if we restricted the trust region to be a very small area, then in this case, the curvature information, we can neglect it, okay? So we drop the second order information and we only need the linear term of the model function. In this case, we can get the P star is approximately related to the gradient, okay? In other words, when the radius is very small, we just use the linear approximation for the model function. So for the intermediate delta between very small size to very large size, actually this P star delta follows a curved trajectory. Okay, so let's illustrate this by the following figure. Now let's take a look at this figure. So we put a dotted line here to demonstrate the trust region, and we are currently sitting at the point xk. So notice that at this moment, we are trying to change the trust region radius delta, okay? So for each delta, we put out its optimal solution P delta star, and we set them to get this dotted line curve here, okay? So this dotted curve actually is the P star delta, all right? For example, if I draw a trust region circle here, the intersection of this curve actually represents the optimal solution of the subproblem will be here, okay? So if we get a bigger trust region size, we may get an intersection here. So this point represents the optimal solution of the subproblem. So from this way, we actually get a dotted curve for the optimal solution with respect to trust region radius. Then, what is the dogleg method? So the idea of dogleg method is that when the delta is very small, we try to use the steepest descent direction to do the approximation. For example, when delta is like this, a very small trust region, then we just take the steepest descent direction. Okay? It is very similar to the optimal trajectory here. And if this delta trust region is very huge, then we just take the full Newton step, okay? And between the two sides, we use a dogleg shape, or we use two line segments to approximate the optimal trajectory. This will become the dogleg method. So it's kind of a leg, all right? So that's why we call it dogleg method. Now, mathematically speaking, we put the dogleg method in a mathematical way. So we define two directions. The first one is sort of line search direction, or the steepest descent direction, because we got coefficient here and the gradient, okay? So it represents when the radius is very small, we move along this direction, all right? And when the radius is very huge, we use the second line segment. The second line segment is starting from this point, and we move toward the full Newton direction, okay? So this becomes the second line segment from PU to PB. then the optimal solution of dogleg method is actually like this. We construct manually a function p tilde tau to approximate the optimal trajectory, and this is our dogleg path, okay? So the intersection of this dogleg path with the truss region radius will be the optimal solution of our subproblem. So in other words, in each iteration, we actually solve the following problem, okay? We have defined the dogleg path p tilde tau here, where this tau is actually a variable, all right? And we try to minimize this p tau tilde in terms of model function. Then this will give us the dogleg method. In other words, dogleg method is also a one-variable method. However, it does not move along a straight line. It has two line segments, okay? So it provides more choices for us to get a local minimizer. Now, let's make a brief summary about this part. In this part, we mainly discuss how we can solve the subproblem. We discuss the Cauchy point, which has explicit form to calculate, as well as the dogleg method, how we design the dogleg method, and what is the subproblem in dogleg method. Okay, so we stop here and see you next time.